Okay, everyone see it all right?
It's not coming up quite yet.
Have you, no? Okay, let's try again.
Should be the share screen.
Yeah.
I think that's happening. It's coming up now.
Okay, yeah.
Okay, Diane, I will hand over to you, and brilliant, and I'll kill my video, and yeah, away you go.
Great. Okay, good evening, everybody. Thanks very much for joining us. Thanks for the introduction, Jonathan, there. My presentation this evening is, it assumes no prior knowledge. I have to say as well, we're all getting used to doing things this way, so I have to excuse sort of issues that crop up. As Jonathan explained, we're going to have a Q&A, a question and answer session at the end. If there is anything pressing, Liam will interrupt things and I can recap on things as needed. As I say, this session assumes no prior knowledge. So what would be good to know is where people are coming from already. So we've got a quick poll to just check while I do an introduction, a quick poll to sort of see where people are from already. So if you could just have a go at that, that would be great. And I'll just... Okay, great.
Okay.
Lovely.
I'll
Thank you very
end
much.
the poll. You should be able to see it.
Right. Great. Okay, so lots of you know a little. That's great. Okay, well, hopefully we can cover more this evening. So Jonathan's already explained a little bit of my background. I do quite a bit of stuff on air tightness and looking at the energy consequence of air movement in buildings, some stuff on thermography as well. I suppose what I do has sort of evolved over the time that I've been working in the field. I started as a householder wanting to understand the building I'd got. So it's a process of evolution, all this is. So we all start from the beginning at some point. What I want to do first of all is talk about what air tightness is all about, really. And underlying air tightness is something called infiltration, and that's the unwanted airflow that we get in buildings. So it's not the deliberate stuff that we really need, it's the other stuff that's taking place. This picture is a really useful picture because it's a really good illustration of the sort of points that we're talking about. It could be through your loft hatch, it could be at the junction of the wall and floor, it could be where the electricity cables come in through the back of the box, it could be around doors and windows. The key thing to emphasize is it's the uncontrolled stuff. It's the thing, it's not the deliberate stuff that we actually need to do, we need in order to maintain good conditions. So what air tightness is all about is quantifying that. And the way that we normally do it is using something called a blower door test. And the picture on the left-hand side is of a blower door in situ. And what that does is to create a pressure difference between inside and outside the building. We get sort of a couple of things from doing that. One is that we get a measure of what the building itself is like. And also enables us to look at other aspects where it's actually coming in, so the detail of where the infiltration is. So the two pictures on the right hand side are using a thermal imaging camera. This is while the blower door has depressurized the building below outside pressure. So the fan has taken air out of the building. So what happens is air gets pulled in through cracks and crevices and all those places we were looking at before. And we're seeing a picture then of where that air is coming in. So on the top picture on the right hand side, that's at the junction of a wall and floor. And it's colder outside than inside the building. So what we're seeing there is fingers of sort of cold air being pulled across the floor, and that's creating that pattern. We're not actually seeing the cold air itself. We're seeing that how the cooler air has chilled the surface itself. And in the lower picture, we've got a loft hatch where we're pulling cool air in around the frame. It's a board just sitting in a frame, so it's sort of your standard traditional loft hatch. And we're seeing the cold air coming in again as fingers cooling the surface of the loft hatch board. So there are other ways you can measure infiltration, but a blower door is the most common method, not only in the UK, but in other countries as well. It's easy to do. It's not a lot of disruption to the building. So that's why it's the most commonly used method. So why is air tightness important? Well, I mean, if we've got all this unwanted air moving around in the building, then we're basically increasing energy use. Now, the thing about air is it actually takes relatively little energy to heat air compared to sort of other materials like water or concrete or brick. But it does increase the energy use. The fact that with this infiltration, what happens is the air change rate in your home increases. So what you find in some buildings is they're particularly difficult to heat in cooler weather, and in windier weather, because what happens is the wind forces the air to change through the property more frequently. So your heating system physically can't keep up. So that's so infiltration increases energy use. Another problem that we have is that this infiltration can create what's called a thermal bypass of insulation. So you could have a situation where maybe you put external wall insulation on the outside of a building, but the detailing maybe at the base of the wall or at the top of the wall is poor, and actually air tracks into the wall behind the external wall insulation. So what that means is that insulation is in effect bypassed. The air moves around it, and so you don't get the performance of the insulation that you expect. Another problem potentially with air tightness is that I mean, the diagram I showed initially showed sort of air moving into the building, whereas in reality what happens is some air on the windward side of a building, you get air ingress, and on the leeward side of a building, you get air leaving the building. What happens in that instance is where the air is leaving, it's going to go from a warm space, it could be relatively humid air, and then it's going to go into this cooler building fabric. And that might result in condensation, which would be a particular problem if you're talking about timber frame construction, where you're going to potentially get condensation where you don't want it to be, which could shorten the lifespan of the building or that particular section of the building. Another thing to bear in mind is that air tightness could affect the performance of ventilation systems. So particularly where you're looking at maybe mechanical ventilation with heat recovery, which is being put into an awful lot of retrofits, you may find that if the building is too leaky, there'll be two consequences. One is that the air movement that's planned really doesn't happen in reality. So you might get airflows sort of that should go from a bedroom into a bathroom for extraction. But because of infiltration, it tends to just be pulling it through maybe a problem related to a soil pipe in the bathroom and then extracting it out. So you may not get the routes of ventilation. So you may get poorer ventilation, or the ventilation isn't as planned. And also in terms of heat recovery, if it's actually just drawing it through on a localized basis, you may not get the level of heat recovery that you would be expecting. So it's really quite important, air tightness is, from a number of points of view. If we think a bit more now about how we quantify infiltration. So just to recap, infiltration is what is happening under normal circumstances, and air tightness is trying to quantify that infiltration. So I've already touched on the fact that we use a blur door test, and the whole point of the blur door test is to measure what the fabric itself is actually like. So when a building is tested, when a blur door test takes place on a building, deliberate points of ventilation are covered over. So they're in effect excluded from the test. Now you can argue, well, is that really the right thing to do? Because we're not getting a complete picture there. This is the method that's used with new build dwellings, and a lot of the tests I do, I test new builds, but I also test existing buildings, and a lot of the I use the same methodology for existing buildings, because what we want to do is we want to know what the underlying fabric is actually like. We can then add back in the additional things like open fireplaces and other things. But what we need to do first of all is to understand whether how the fabric itself is performing. So these extra things are all excluded from the baseline test. Now, when I'm doing a test on a property, say a property for a refurb, I would look at other things that are at play, and I might do additional tests to see what impact they have. For example, I did a test just before everything shut down on a property which is being used as a trial property for a landlord who has a large number of dwellings, and they'd got secondary glazing fitted in this property. It's a 19th century property, and we looked at the impact of the secondary glazing, which actually was very good in that particular instance. It made a difference of about 10% on the leakage of the building as a whole. The windows themselves were secondary glazed behind it. So you can use the test to sort of explore different things, but the underlying test is for the fabric alone, with these points excluded. So there's two measures for air tightness that are used. Air permeability is the most common one that's used in the UK, and air changes per hour is also referred to. So just talking a little bit about what they mean. Air permeability is the flow rate that the fan actually has to create to maintain a pressure difference. So the easiest way of thinking about it is looking at the units. So we've got this fan that is moving air in meters cubed per hour, and we're trying to maintain a pressure difference between inside and outside the building. In the UK, the standard pressure is 50 pascals pressure difference. Now that pressure difference equates to the equivalent of sort of a 20 to 30 mile an hour wind. So the units that we're dealing with for air permeability are meters cubed per hour at the 50 pascals pressure difference, divided by the surface area of the building. So we're talking about the floor, the walls, and the upper surface, whatever we've got at the roof line, whether that's a flat ceiling or a vaulted ceiling. So it's the meters cubed per hour, which is the fan flow rate, divided by the surface area of the building in meters squared. In terms of air changes per hour, we don't use that commonly in the UK particularly. Things like building regs, so Part L, refers to air permeability, not air change rate. But the air change rate is actually easier to relate to as a sort of a building user, because what we're talking about there is the fan flow rate related to the volume of the building. It's more straightforward. It's meters cubed per hour divided by meters cubed of the volume. So it's just an air change rate at 50 pascals. Now that's more commonly referred to when you're thinking about passive house standards. And an air change rate is used there. It's calculated in a slightly different way to how we'd calculate it in the UK, but we can leave that for another time, really. So air permeability is really the key thing. But if you're talking to somebody about air tightness, what you need to do is to confirm what units what measure they're actually talking about, because often it's not clear, whether that's in a general conversation or people will just say, oh, it's 5.5. You need to ask them about units so you know whether you're talking about air permeability or air change rate, because they can be significantly different. So we've got two buildings here, two houses. We've got an L-shaped bungalow, and we've got quite a boxy detached house. Both properties are detached. I'm trying to illustrate the difference between air permeability and air change rate. Now, if we assume they've both got the same air change rate, could you have a quick guess as to which would have a better air permeability? So, Jonathan, if you can put up the next quiz, that would be great.
Should be able to see it now.
Very interesting. Yeah.
Last one or two.
Okay.
Okay.
Brilliant. Thanks everybody for participating. It's great. Okay. So that's really quite interesting, that people feel the house would have a better air permeability. So just thinking about what we've got. So the house on the right hand side it's quite cuboid, it's quite boxy, and the thing about that sort of cuboid style is the surface area and the volume are roughly the same. So you'd probably find if that one's got an air change rate of 5, its air permeability would be about 5 as well. Now compare that to the bungalow on the left-hand side. So it's got an air change rate of the same amount. But the thing is, because it's a bungalow, so it's an L-shaped bungalow, it's got loads of surface area. So what that would actually mean is, because it's got this much bigger surface area, you're dividing that same flow rate by a much larger area. So actually the bungalow would have a better air permeability because it's got a much larger surface area. So we need to think about the form of our building as well. Not that we can do much about that in a retrofit situation, but again, one of the key things when we're thinking about passive house is loads of emphasis is put on the form of the building, because the less sort of outside surface area you've got, the easier a building is to heat. So if you were in the fortunate situation of being able to build your own home, then thinking about that form, minimizing the surface area of the building, is really key from an energy efficiency point of view. Oh, why won't it move? Oh.
You might need to click into the PDF rather than the presentation of the PDF.
Okay. Great. Okay. So what I'm going to talk about now is give you a better idea of benchmarks, that things, because it's quite an abstract concept really. Trying to get a feel for what we're talking about when we're talking about air tightness levels. Now, I'm going to go against what I was just saying about not mixing up air change rate and air permeability. But the passive house standard is something that people have commonly heard about. And I mentioned with that, you have to hit an air change rate of below 0.6 at 50 pascals to achieve the passive house standard. So if we think about that house that we were looking at before, that boxy house where roughly the surface area is the same as the volume, then that would have to hit about 0.6 to achieve passive house. In actual fact, that boxy house that we were looking at, that got 0.3 as a result. It's not a passive house, but the self-builder that built it took on lots of passive house principles, so that got about 0.3, so well within the passive house standard. If you think about where we are generally in the UK, the Part L of building regs, which sort of governs air tightness requirements, has a limit of 10 meters cubed per hour per meter squared at 50 pascals. It's very rare these days to get a house that has that at the limit. The thing to emphasize here is that the smaller the figure, the more airtight the house is. What you find more commonly is that buildings have to achieve a standard somewhere between about 3 and 8. This is for new builds. In order to pass building regs. And a typical estate type, 3-4 bed detached would usually, they'd be working to a requirement of having to achieve about 5 as a maximum. So a figure up to 5, typically between about 4.5 and 5 is what's normally achieved. But if we start to look at sort of below that, if you're thinking about doing something serious from a ventilation point of view, say fitting mechanical ventilation with heat recovery, there's a threshold at about 3, that's an air permeability of 3, that where you need to be looking at ventilation systems, so mechanical ventilation with heat recovery, or something called mechanical extract ventilation. From a building regs point of view. There's also a view that in order to see your money's worth out of an MVHR, you really should be looking at below 1.5-ish from an MVHR point of view. So that's sort of even tighter than what Part F is looking for. So that gives you a context for the sort of tightnesses that we might be looking at. So we have another quiz now. Okay, so these are all buildings that I've tested. Give you a little bit of background on them. So what we've got here, this is a semi that I'm pointing at initially on the top left. It was built in the 1930s. It's well maintained, but nothing exceptional done to it. No particular sort of unusual upgrades. We've got the property on the top right is, I tested it within the last month. It's a new bed, four-bed detached property. The one in the bottom right, I tested earlier this year. It's a new build. It's got all sorts of gadgets and gizmos. It's got PVs. It's got an air source heat pump. It's an end terrace. It's block built cavity wall construction that's stone clad. And the one in the bottom left is a 19th century cottage, a semi, and it's in an unrefurbished state. So the question I would like to ask you is, which do you think of these has the best air permeability? Very interesting.
Last few people. Now or never. Okay.
Great. Well, thank you very much for participating. That's really good. Okay, so let's talk a bit more about these things. One of the things I've learned as I've sort of gone through my processes with testing is you cannot always judge things you can't judge a book by its cover. So what we've got here, the worst performing house of this group is actually this is the 1930s semi, and that has an air permeability of just under 15. So quite a long while ago now, I did some research I did lots and lots of tests on existing buildings, and what people told me before I started that research was there'd been very few tests done on existing buildings. And what people told me was that they were expecting older properties to be roughly twice the level of them to be twice as leaky as new properties. So air permeability wise of the order of 20 was what people were telling me, but nobody had actually gone out there and tested properties. The handful that had been tested were pretty, they weren't in good states of repair. There were ones that were due to be refurbed. And I was interested in looking at, well, what are houses like that people typically live in? So this house, this semi is a typical one that somebody lives in. Got decent amount of loft insulation, not been mucked about with too much. So that was at 15. That's probably about where people would expect a property to be. So that's the leakiest one on here. The next leakiest one is the one down in the bottom right-hand corner, this new build that's got all these gadgets and gizmos on it. And that really is down to, that came out at just over 6. So it complies to building regs. It had to get a figure of under 7. So it complies to what's needed from the design SAP calculation. So it's past building regs, but it's at 6. In terms of the next leakiest one, it's this old cottage here. Now, that property came out at 5.6. Now, that is one of the best results I've ever had on an existing building. This property has not been mucked about with its original plasterwork. It has an extension on the rear that was put on sometime after the war, but it's been really well built. It's a solid brick construction. But the reason for the test was because there were plans to upgrade this and a group of other properties that are identical to it or very similar. And the reason for the test being carried out was to benchmark it. Well, how leaky is it? What do we need to do to make it more energy efficient, to improve its carbon footprint? So it's quite interesting that that property is really quite airtight. Well, not quite airtight, but even compared to what the requirements are on new builds, it's got a good result. It's not airtight compared to a passive house, but you know, the result on that property could have been expected to be 20, say, and it's actually a bit over 5. So that in itself is sort of changing the strategy with that building, because what they've got there is something that at the moment is reasonable, and they need to build, the property owners need to build that test air tightness into the calculations and plans that they've got for the upgrades. So this building on the right, this new one, this top right hand one, this detached 4-bedroom, is actually the best air tightness there. But in saying that, it's 4.9 air permeability. So it's not massively better than this cottage here. And this house was built last year. And this house was built more than 100 years ago, and it's had 100 years worth of wear and tear, and it's only just a bit leakier than this new build house. So I'd just like to look a little bit more about the situation with this new build house. So this is an image I took inside the property. And though it's not showing air leakage into the building, you know, those fingers of cold air that we were looking at before, it's a really good illustration of one of the problems that we have, both with new builds and also when we retrofit properties. And what we've got here, so the thermal image on the left-hand side is showing the daylight image is on the right-hand side, and we're looking at this corner here. And what we can see here is the building is block construction, and then it's dot and dab plasterboard inside. So just to explain, when plasterboard is fixed, you have dabs of plasterboard adhesive holding it to the wall. And when plasterboard should be edge sealed, so around the perimeter of each board as it's fitted, it should be sealed all the way around the edge. Now, it's quite difficult to do when you've got things like plug sockets and stuff. But what we can see in this image is what's happening behind it. So this image is taken with the building is depressurized below outside. It's warm inside, it's cold outside the building. But what we can see here across the top of the thermal images is we can see these dabs of adhesive. We can see that then it's not continuous. And what we're seeing is the cooler air. It's on the first floor, this image. The cooler air is being pulled down from the roof void behind the plasterboard, and it's bypassing the insulation that's in the wall. So the cooling here is to the extent that in this new build property, under normal living conditions, so 20 degrees C, say in the middle of the room, 50% relative humidity, at points, they will be getting mould growth in the winter on this wall. So it can have quite serious implications. So in this case, we're not only looking at the insulation being bypassed, but we're also looking at risk of mould growth as well. And one of the things is when we're looking at retrofit is quite often dot and dab plasterboard is something that's commonly used. It's routinely used in new build, and the impact of it just doesn't seem to be appreciated. And it's one of the pitfalls we need to try and avoid with retrofits, that we either use a continuous layer of adhesive all the way around the outside. There is still a risk because the blockwork itself is air permeable, that you will get some thermal bypass. So the best idea is to have a continuous layer. If you're going to use plasterboard, to have a continuous layer of adhesive behind the plasterboard, or that the underlying wall is treated with, say, an air tightness, a paint on air tightness layer. But that's a good example of showing what thermal bypass looks like. So if we think about our older buildings, one of the key things we need to appreciate is it's the presence of the plaster that is keeping the air out. All our common building materials, so blocks, sort of standard bricks, stone, rubble construction walls, they're all air permeable, and it's this layer of plaster on the inside that keeps that reduces the air movement. So what we want to do is if you're thinking about air tightness on your home, is you need to start thinking about the places where this plaster is not continuous or where it's broken. So things like what's happening at the skirting board. You know, skirting boards are there to sort of disguise the plaster stopping short of the floor. What's happening in the void between a ceiling and the floor above, where the joists go into the wall. What's happening where it's coming up through the floor. So think about those areas. Sort of a fundamental thing is to think about those areas where you haven't got plaster actually on the wall. So moving on a little bit to think about how we can achieve air tightness. And there's really sort of four key areas to think about. One is knowing where you're starting from. You've then got to decide where your target is, develop a strategy then, and then look at workmanship and quality assurance when the work is actually taking place. So talking a little bit more about each of those points. Knowing where you're starting from is really quite important, because I mean that example we were looking at before of that cottage, you know, if you'd got something that was like the 1930s semi, say, instead of that cottage in terms of air tightness, you could have a completely different strategy. So in terms of where to spend your hard-earned money, looking at knowing where you are is really quite important because it governs your approach. So say you test your house and you find actually you've got really quite good air permeability. That might send you more in a direction of thinking about your ventilation strategy and putting more emphasis on you investigating that or more money into that area. Whereas if you've got a building that is very leaky, clearly you would want to direct things more towards thinking about how you can do the airtightness and also how far you could possibly take it, because there's clearly some things are going to be harder and more costly to deal with. So the property I'm showing you here is it's a barn conversion. It was converted at some point in the 1990s. And I think one of the reasons for talking about this is you can't assume that the leakiness of the building relates to the age of the property. So this property was horrendous in terms of air tightness, somewhere in the 20s. Air was tracking all over the place. And what we've got with the building is we have the original barn conversion, and then we've got two extensions to the rear. The one with the pitched roof is where the thermal image is on the right hand side. And that was done in the early 2000s as the family in the house grew and they needed more space. And actually looking at it with in more detail with a thermal imaging camera, this again was taken when the building was depressurized. You can see we've got all sorts of air leakage, we've got missing insulation in the ceiling, there's all sorts of problems. So in testing this building, you've not only looking at, well, where is it standing, you know, in terms of putting a figure on that air permeability, but also looking at the detail, because then that can direct you very specifically into, okay, well, what do we need to tackle first? What are the big factors with this property? So it's a real help to actually consider testing the building before you start, because then at least you can spend your money wisely. I've already sort of covered this property a little bit, and again, they're using it, it's a benchmarking test before refurbishment. So they have changed that, or they are changing their strategy with this building as to what they plan to do. But this property is one of 500 on this estate. So what's been learned from that property, you know, clearly it can be replicated on others. The second thing is to decide what your target is. And I think this is the hardest bit. So you've had a benchmark test done, and then you've got to sort of work out what you're going to do. And everybody's trying to sell you something. You know, you're looking at heating systems, you're looking at all sorts of stuff. And there's a temptation to jump this almost, to get stuck into it and get started on the practical stuff. But the thing I found is that if you don't do this stage, then it's disappointment. You sort of it's likely to lead to disappointment because you don't know where you're trying to get to. So, you know, for the project managers out there, what we're doing is we need to know where we're starting from, and then we need to know where we're going to. And then again, you can make sure that the steps that you're taking are all get you towards your end goal. So that you don't get distracted on that heat pump that you thought you might want. You need to really think long and hard about what your target is and try and quantify it. So a bit of background about me. So I get to do investigations, retrospective investigations into buildings. So things go wrong, yes, why isn't that performing the way that it should? So that detached house, that new build detached house I was showing you earlier, is a retrospective investigation for me. The clients bought it, well, they moved in autumn last year, and they can't keep their nursery warm for their toddler. And they wanted me to look at it. The bad news is I found a lot more wrong with the property than they were expecting. Unfortunately, it probably complies still to the airtightness level that's needed. But there are a lot of issues with that property, things they need to take back to the developer. But so I do quite a lot of these investigations, and the ones where I've done where the client, hasn't got what they wanted, it's a refurbishment and they didn't get what they wanted from it. Their energy bills were higher than they expected. The thing that I realised, having gone through the process a few times, was they hadn't quantified what they were trying to achieve. So the client thought they'd said to the architect or the building designer or the builder, this is what I want, and had been quite specific about it. But the architect hadn't heard or had misinterpreted what the client had said, or the client hadn't said it clearly enough. So that process is really frustrating. So as a result of going through that a few times, I realised what I needed to do was to feed further up the supply chain. So that's what really prompted me to train as a passive house consultant, because people weren't quantifying their expectations. I'm not talking about on passive houses, I'm talking about on refurbs. They were in the sweetie shop and picking the things that what they wanted or the architect was suggesting, but actually they weren't looking at, well, where does this actually get me? So trying to work out what your target is really important. You can do that yourself. You can get somebody else to help you to do it. I mean, a really good tool that I use is what's called Passive House Planning Package, which is quite cheap to buy, so 100 odd quid to buy. If you're into spreadsheets, you'll love it. And that would help you to play around with different options on your home. You can model it and look at options that you've got, or you can, you know, pay somebody to do it really. But understanding what your target is really important, because when you understand that, you can make sure that's communicated to everybody else that's dealing with it. So in terms of then developing a strategy, it's got to be designed in to what you're doing, whether that's a new build or whether it's an existing property being refurbed. You've got to, you know where you're trying to get to, then you've got to make sure that all the steps that you take are getting you in that right direction. And it's not all about fancy materials. Most of it is about workmanship and being clear about what you're trying to achieve. So a key part is to develop an air tightness strategy for the building. So you can do this yourself. All you need is a sketch floor plan or a sketched elevation of your home. And what you need to think about is what is happening at every single junction that I've got in my home, and how is that being dealt with from an air tightness point of view. Now, clearly, the extent that it depends on how far you want to take the property. If you're talking about Retrofit, which is the sort of refurb, it's a slightly relaxed standard under Passive House for buildings that are being refurbished. So if you're looking at something like Retrofit, then that's clearly different to, I just want to make my house warmer and I'm on a really tight budget. But this is a value, whatever standard you're looking at. And it's something that you can do yourself and just think about, well, what's happening at each of these junctions, and at any point where I've got anything going through the wall, floor or ceiling. One of the most common things I see is inset light fittings, and in large quantities, and they invariably leak from an air tightness point of view. And something like that, if you actually sit down and sort of sketch it through, you think, well, actually, are they the right light fitting? Maybe something that where it's dealt with slightly differently. I know aesthetically they're great, but in terms of air tightness, they're not good. So have a strategy, get your sketch plan, and just think about what's happening at every junction and at every point where the air tightness layer is breached. So in terms of how to achieve it, it's really down to being clear about your goals and your specifications. So going back to that second point again, you need an air tightness champion. This is what's sort of used on sites where you're trying to maybe a development of a number of relatively airtight houses. You have somebody who takes responsibility for it, who drives it, who is passionate about airtightness. You can be that person. You just need to convey the importance of airtightness to whoever's on site, and emphasize to people that everybody's got a responsibility. It isn't down to whoever sticks the tape on. It's everybody has a responsibility for airtightness in the building. Again, being clear about what your goal is really important. And having a culture where it's not about blame. What you need to know is if somebody has accidentally drilled through something and created a hole, you need to know about it so you can do something about it before the kitchen goes in. So avoiding this blame, but making sure you've got this clear goal is really, really important. So they're the 4 steps really that you need to follow with your project, whether you're doing it yourself or whether you've got it's something where you've got contractors in doing it. Last thing I'd like to talk about is we can't look at air tightness on its own. This property, it's a 1930s construction. It's a semi again. It had a benchmarking test initially before the refurbishment that was coming out sort of low 20s, so relatively poor. It's suspended floors, quite a lot of widespread issues. The bays on the front are just timber frame, slate hung. There was loads coming in through there. Post refurb, it came out about 4.5, I think, in terms of air permeability. But the thing is that the ventilation really wasn't looked at seriously enough. And key to it was, this is the unit that's, the middle photo is the unit that was fitted in the bathroom, which is what's called an MEV, mechanical extract ventilation unit, which is designed to operate in more airtight buildings. But the thing is that actually the filter on it was really fine. So this lower picture on the right hand side shows what the filter's like. But the one above it shows how clogged it got before it was cleaned. The one below is after cleaning. It's a really fine filter, and this is a rented property, and they were suffering problems with moisture and condensation in this property, because although the air tightness was addressed, the ventilation hadn't been properly addressed in this instance. And in retrospect, it should have been a more detailed plan. This property isn't alone. You know, I've seen another property earlier this year where the householder has refurbed the property. They've fitted external wall insulation, and they've clearly cut the airflow in the building to such an extent that they started to get mould on the bedroom that their children slept in. And that was down to really inadequate ventilation from the bathroom. It was moisture transferring from the bathroom into their children's bedroom, and condensation occurring on what was a remaining thermal bridge. So it's really important that you don't just look at air tightness, you look at ventilation as well. Okay, so that's me on my presentation. So
fantastic, thank you, Diane. Really great. I don't know, Liam, whether have you got any questions or observations you want to ask to kick us off?
No, it's a really interesting presentation. It's always interesting hearing it from a slightly different perspective, because I've always gone in on it from completely the builder side of things. I was just wondering what your views were on design, and how important it is to make sure that the design of the air tightness has actually been put into place before you get people onto the site.
Oh, it's absolutely key. I think there's a danger with new build dwellings as well, that people don't. It's passed to the builder, unfortunately, in lots of cases. And I think if the builder is experienced, then that's not so much of a problem. But the thing that we're dealing with quite a lot is that not all builders are experienced, not by a long shot, really. So in terms of the least risky approach, getting it designed beforehand, whether that's you at home with your sketch drawing and your red pen working out your air tightness strategy, or you getting some further help to do it. I think even if you're dealing with an experienced builder, you'd need to verify yourself with that builder that they are going to do what you want them to do. So having that discussion about what is your objective, how, in terms of air tightness, are you looking to get something that is NFIT standard, or are you just looking to get rid of the worst drafts, or somewhere in between? So clarity of your objectives and having that discussion with the builder, that they understand what your objectives are, even if you're not dealing with an intermediate professional, whether that's an architect or somebody else.
Yeah, because I know on some deep retrofit stuff, because I've worked in the role of air tightness champion on quite a few projects. And quite often you can, if the design isn't there in the first place, it ends up with the builders being the ones stuck with the difficult conversations because it hasn't been worked out.
It really is such a common problem, and we've got to sort of we have to stand our ground a bit, really. I mean, I like the passive house methodology in that it forces you to design before you start work, because you won't get there. And I think we have to be quite firm. In an ideal world, we should sort of be able to turn around to the architect or whoever's doing the specifying and say, no, we're not going to start until this is clarified, because all you're doing is you're putting problems further downstream that you're going to it's going to come back and bite you. Basically, you are not going to get what you want. And in so many instances when I've done these investigations, that's what the problem is. It's not been quantified and it hasn't been properly detailed.
Yeah,
sorry, that was a bit brutal, really. No, it's a really problem.
I completely agree. Air tightness is so often an afterthought, even when it should be one of the most important things, particularly in deep retrofits. But anyway, we could rant over this.
There's another.
Have we got any questions?
We've got a couple of questions already, and I would just encourage people to put questions in the chat, and we'll open up the microphones if you've got them as well.
Could we do the quiz as well, to see whether people want more information on it?
Yeah.
Do they want more webinars?
Let's do that after the questions. Okay. There was a question which Liam did answer in the chat, but when you're using the term good air permeability, does that mean good as in lots of it, or good as in managing it well?
Managing it well, yeah, it's a difficult thing, because it's how, I suppose, I've tried to use the terms best. It's better to use a number. That's the thing. But with this being an introductory thing, I was concerned that I didn't sort of just waft too many numbers around, because, again, it's better to speak about a specific number, because one person's, if you get an air change rate, say, of 1, somebody might say that's great, but if you're aiming to do a passive house, it's a problem. So quantifying it, keeping it as a number as much as possible, really.
Great. Liam, do you want to open up the mics for the people that have posted questions in the chat? Liam, or maybe Liam's.
He's got his mic switched off. Liam has. It's Margaret.
Question from Margaret. Shall I open Margaret's microphone then? Or
yeah.
Well, sorry, I can see.
Sorry about this. I was waiting for hands up, and then realised that there was none.
Sorry, we didn't say that. You can put your hands up, but there's also some in the chat. We've got one from John, one from Margaret, one from Stella. I'll open the chat for Stella to ask her question. Can you hear us, Stella?
Yes.
Fantastic. What's your question?
It was towards the end of the talk, Diane pointed out the real problem, which is that you can go for air tightness, maximum air tightness, but what about the ventilation as a result? Because if you don't go for passive house and have VHR or whatever it's called, then how do you address that problem of air circulation, controlling air circulation?
It's a real issue. And again, it depends on how far you're trying to take it. One of the problems is the variability. If we're looking at other ventilation, it's the lack of control, really. So I do quite a few investigations using things like these, so that, relative humidity temperature data loggers. And I used to be quite a skeptic over MVHR, going back quite a long way. And then I realised, that the whole point is you've got something, it's controlled. It's controlled, the amount is controlled, and the delivery point is controlled. Everything else is really poorly controlled. So if you look at something like mechanical extract ventilation, which is the alternative to MVHR in more airtight buildings, the problem you've got there is it relies on the use of trickle vents. And if people have got their trickle vents closed, they're not going to get the ventilation that they need. So it's an issue. I think, perhaps when we look back in 20 years, we'll sort of see this as a transition. I think we're going to have to put more MVHR into properties, or we take a different approach. I mean, for example, in other parts of the world, Germany, they traditionally have a different method of ventilation. They don't have a, as we'd have extract fan, intermittent extract fans in our, bathrooms. They would do like a purge ventilation for 10 or 15 minutes a day. So they don't have extract, you just throw all the windows open for a short period of time, then shut them all. But they have a problem in that people aren't doing that anymore. So it's a really, it's a problem. There's various things you can look at, but there are things that can go wrong, more easily wrong with other options, like trickle vents not being open, or if you're relying on window opening. So it's difficult.
Okay.
It's just that you do have a lot of disruption if you try and put it into an older house. Mine's over 100 years old. Trying to put MVHR into a really old house is just so disruptive.
There's other options. It's an area where there's development. So use of single room ventilation units is an option. So they're sort of like wall fans that have a heat recovery within that. You have sort of push and pull systems that you have a paired unit that sort of push it through for a period of time. And then reverse it. There's all sorts of options out there. There is a lot of development. So maybe that's another webinar.
Yes, thank you.
Okay, brilliant. Thanks, Stella. Let's move on to Margaret then. You should be able to talk.
Yes. Can you hear me?
Yes, can hear you loud and clear.
Good. My question was simply about inset lights. Is there some way to create some kind of air tightness over the top if clients insist on having them? I've got some clients who've just put some through the air tightness membrane.
Oh no!
Yes.
Okay. I think it has to it's sort of understanding the context really. So if you're wanting to put inset light fittings through an air tightness membrane and it's aiming for passive house, it's not a good idea.
No, it's not passive house, but it just they didn't really think that through. And I didn't catch it soon enough. Just to say, in that same house, which is 1860, we were able to use demand control ventilation. And now it hasn't been handed over yet, but it's very neat. So I conditional hope here that it's going to prove to be the right answer.
Okay.
But then, of course, if they penetrate the air tightness membrane, we won't need to worry.
I think in terms of what you can do measures wise, if the inset light fittings are in the top floor of the building, there's various cowls that can be, you can fit a cowl over the top that can be sort of sealed to the plasterboard ceiling, and then insulation can be laid directly over the top of that. They are definitely a help in terms of reducing their impact, but it's still, you're trying to get over something. It's like other decisions. It's like, choice of glazing and everything else. I think trying to get people to understand at an earlier stage the consequence of that decision. If they want it, that's fine. That's at least, but understanding that it's their decision really. But the cowls are really they're commonly stopped by electrical wholesalers. That would go to the back.
The roof of a bathroom, and it's quite a low ceiling, so I can see how we got there. Just a little distressing. Anyway, thank you very much. Excellent seminar. I must go.
Thanks, Margaret. Really good to hear from you. I think Liam had a point on this as well.
Yeah, there is one product that is quite useful for that, which is sold by Green Building Store, and it's called Optime, and it's one of the cowls that Diane was talking about. It's not technically meant to be used in a bathroom scenario. However, if you've got a service void, where it's counterbattened below the membrane to the plasterboard, you can fit them because then you've got a ventilation gap and they can go straight through the membrane. It's like sit on top of the membrane.
I don't think we have that depth. Yeah.
Thank you. Okay.
Cool. Thank you, Margaret. We've got a question from John, and then we'll have one from Caroline as well. And do put more in the chat if you have any. So, John.
Yes, good evening, Diane. How would you raise standards in the construction industry, particularly regarding retrofitting and, individual terrace properties? I mean, a lot of the times, you're dealing with people, one man and his van and his lad. And, it's just a case of they're quick in and quick out.
I think that is definitely another session, but again, going back to you being clear about your goals, and if you're clear about it and you talk to your potential contractor about it, if they really don't get it, they are not the people for you, and it becomes very clear if you're talking about specifics. So you've got your sketch floor plan and you've done that red line. Roughly where you're aiming to be in terms of air tightness. Say you're aiming to try and get your building down to 5. If you're talking in that way to your contractor and they really don't get it, it will become evident very clearly. I have to say personally, I occasionally test standard new builds sort of for builders when they're doing one-offs, custom builds really, and I treat each one as a training exercise. And what's really pleasing is that people get it. Not everybody does, but a reasonable proportion of people get it, and it's simply because they've never had to look at it. They never had to get involved in it in the past, and most people, reasonable proportion of people are receptive. But until clients are demanding it, they won't do it. If they know they won't get the work, then they will eventually realise they've got to do it.
Brilliant. Okay, thanks, John. We've got another question here from Caroline.
Yeah, so I guess we touched on this just now, but so you need to get this balance correct and you need to decide your targets. But how, as a layperson, do you know who to trust and therefore how to decide what your target is? So you said you'd set a target of 5, an air tightness of 5, but without getting swayed by those professionals who are trying to sell you something. And how do you even know what's possible?
Okay, in terms of what's possible, that's where the benchmarking thing comes in. I know it's an extra cost, but you get... So if I do a benchmarking test, I would be able to sort of say, okay, it's standing at this roughly now. I think you'd be able to get to that if you do these bits and pieces. So that would guide you, really.
So the benchmarking test includes the kind of where you could get to. It doesn't just say, well, you are here. You also get a little bit of indication about where it could go. Yeah, I mean, the way that yes, in terms of if I go to do a test, that's what I would be doing, because you are trying to understand your building and know where you can take it to. So yes. On the other side of it, Jonathan will have to deal with that.
Yes, and I think we've come to the end of the questions. So I'm going to quickly talk about people-powered retrofit, and then we'll have some polls to finish off. But really, Diane sort of teased out, or the Caroline's question teased it up well, that particularly for those of you living in Greater Manchester or within reach of Greater Manchester, we have our people-powered retrofit service, which Diane is one of the consultants we use on the service. This is an end-to-end service for householders looking to retrofit their homes who are having issues or problems, maybe trying to get a handle on what to do first, or maybe a bit worried about who to trust and who to go to. And we take people through from simple advice, like starting out, thinking about things, through assessment, coordination and specialist assessment and testing, like air pressure tests, through to on-site supervision and working with contractors and quality assurance. So if you're interested in people-powered retrofit, you think, might be interested in that service, or we have some consultants on the call tonight. If you're interested in being part of delivery, do get in touch with me, Jonathan at carbon.coop, and we can set you up with an interview, probably with Liam, to get you started. We have one or two polls to finish off with. First one, Diane, you wanted to tee this up?
Yeah, I mean, we're sort of talking. Right, okay. Okay. Yeah, I mean, I'm bound to feel this is an important area, but it would just be interesting to know, sort of from all of you, whether it's something that people feel they would like more information on, particularly maybe those how-to steps, exploring each of those stages a little bit more.
Yeah, so if you're interested in more, click yes, and we'll go into a bit more detail in some of the areas. I should also say that in putting this webinar together, we've identified the need for a bit of a fact sheet to go out to people that we can just, issue as a starting point. So that's really good to know. That's fantastic that there's definitely interest in that, which is great. Okay, so we've come to the end of the webinar. Really big thanks again to Diane. I really hope we'll have you back again to go through some more of those detailed webinars in the next few weeks. As I've said on the chat, the presentation and a recording from tonight will be sent round everyone who's signed up. It usually takes a couple of days for the videos to be placed online. So yeah, it may be tomorrow, maybe Monday by the time you get that. So thanks again. Thanks everyone who's participated. Thanks very much to Diane, and thanks to Liam. And yeah, keep in touch, and we'll see you all soon. Thanks.
Thank you.